All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Vestandria, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on our boundary to interstellar space, a new regime of space physics. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with the questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Dr. Elena Provornikova is a space physicist at the Johns Hopkins University Applied Physics Laboratory with research interests in the physics of the outer and inner heliosphere. She's the deputy PI on the Heliophysics Mission of Opportunity, Sheila, and is the lead scientist for heliophysics on the Interstellar Probe Study at APL. Professor Ofer is a professor of astronomy at Boston University and the PI of a NASA Drive initiative called SHIELD, which stands for the Solar Wind with Hydrogen Ion Exchange and Large-Scale Dynamics. That is a multi-institutional team with the goal to improve the modeling capabilities of the heliosphere. Professor Ofer has held many prestigious leadership positions, including the chair-elect of the American Physical Society Topical Group in Plasma Astrophysics, and has chaired the Outer Heliosphere Subpanel of the Decadal Survey in Space Physics of the Solar and Heliosphere Panel. Dr. Jamie Rankin is currently a postdoctoral research associate at Princeton University and received her PhD from Caltech in 2018. During her graduate studies, Jamie contributed to the development of the High Energy Particle Instrument EPI-High for the ESIS instrument on board Parker Solar Probe. At Princeton, she continues to study the outer heliosphere and the interstellar boundary using data from both Voyager and IBEX. She also works on Parker Solar Probe and is the deputy instrument lead for the Solar Wind and Pickup Ion instrument on IMET. And with that, Dr. Provornikova, the virtual floor is yours.
Thank you, James, and hello, everyone. So I would like to give a brief overview of the ongoing study of the future space mission Interstellar Probe. With this mission, we will go to the interstellar space and discover what's out there and how does the sun interact with the interstellar medium to form a complex and dynamic bubble, which we call heliosphere. Interstellar Probe will be faster and further than any spacecraft we ever launched. An idea for this mission has been with us for 60 years. Recently, APL has been contracted by NASA Heliophysics Division to do the study how we can turn this mission into reality. It's really amazing then that in the first 2 years of the study, over 200 scientists and engineers from more than 9 countries around the world actively following or providing inputs and ideas into the Interstellar Probe concept study. So what is the Interstellar Probe? Since the beginning of the space age, humanity has dreamed of going to another star. And since 1960s, scientists have discussed of going beyond our heliosphere to the unexplored interstellar space. We are not going to another star, but Interstellar Probe is the first step to the local galaxy. Interstellar Probe will travel through the boundary of the heliosphere into the interstellar medium to about 1,000 astronomical units from the sun. We are not a starship. An Interstellar Probe would be a large strategic mission that uses available technologies to achieve asymptotic speeds by a factor of 2 or 3 greater than those of Voyager 1 and 2 spacecraft who discovered the heliosphere boundary and exploring the doorstep of interstellar medium. The compelling science about the nature of the global heliosphere remained with us over the decades and is completely enabled by going to a new unexplored place. For the first time, we will discover how our heliosphere, the only habitable astrosphere we know today, looks from outside and what lies beyond. Our speakers today, Merav and Jamie, will talk to you about major unsolved science mysteries. For planetary science and astrophysics, there are certainly very unique opportunities for Kuiper Belt object flybys in the outer solar system, and for going beyond our own obscuring zodiacal cloud to open up the window to early galaxy formation. And lastly, Interstellar Probe also paves the way for the next steps on longer journeys ahead in many different ways, scientifically, technically, and programmatically. And next slide, please, James. The key word for the mission study is pragmatic. We have set the high-level requirements to bound the concept study. First, we need to have all technology ready for flight by 2030, which is 10 years from now. We need to have the capability to operate and downlink out to 1,000 astronomical units. And we require no more than 600 watts at the beginning of the mission. And lastly, the mission lifetime is no less than 50 years. Next slide, please, James. So in this image, you are looking at the layout of the solar system, the heliosphere boundary, and the local galactic neighborhood on a logarithmic scale. The solar wind moves supersonically away from the sun, well beyond the orbits of the planets until it reaches the region where it interacts with the interstellar medium. Previous explorers, Voyager 1 and 2, discovered that the solar wind decelerates sharply at about 90 astronomical units, which marks the termination shock. Later, in about 10 years, they crossed the heliopause that separates solar and interstellar plasma particles. The heliopause marks the boundary of our bubble, our heliosphere. As you all know, Voyager 1 and 2 were planetary missions and fortunately became accidental interstellar explorers. Right now, two Voyagers are at 150 and 125 astronomical units from the sun, exploring in situ the very local interstellar medium just beyond the heliosphere. Voyagers will likely operate for another 5 more years. After flybys of Pluto and Kuiper Belt object MU-69, New Horizons mission will explore the outer heliosphere plasma until about 90 astronomical units and has a chance to cross the termination shock. Voyagers uncovered a number of mysteries showing that interactions between plasma, energetic particles, and magnetic fields at the heliosphere boundary mark a new regime of space plasma physics. And our speakers today will talk to you in details about this. For Voyagers, it took 30 years to get to the boundary region. With conventional propulsion, Interstellar Probe would explore this region after 12 years from launch, and in just another 8 years, it will explore unknown regions in the interstellar medium where we've never been before. Next slide, please, James. So the primary mysteries that Interstellar Probe mission is going after is, what is the global nature of the heliosphere? How do the sun and galaxy affect the dynamics of the heliosphere? And what is the nature of the interstellar medium? And now I would like to turn it to Dr. Merav Ofer, and she will talk about our heliospheric shield.
Thank you so much, Elena and James, for the introduction. So I would like to give you an overview, some of the unknowns of the heliospheric that we call the shield, and I will talk why we say that it is a shield. So next slide, James. So we know that most stars, if not all stars, have astrospheres around them. And they come in all sorts of shapes and forms, as seen in these beautiful images that we have. And next slide. So we see them in different shapes around different types of stars, but we have our only example of an habitable one, that is ourselves. We are searching for exoplanets around other stars, but we don't really know what are the conditions to begin life. One of them we know is that all the stars and the exoplanets are embedded within astrospheres. And we have with our own, the heliosphere, an opportunity to study astrospheres in a lot of details that we will be never able to study astrospheres that we can only see far away by measuring light. So one of the things we learned recently, next slide please, is that our heliosphere, our own astrosphere, shields 75% of cosmic rays, up to 1 GeV. And we know that these particles are a key fundamental part of creating life on Earth. And with the passage of Voyager by the heliopause, we learned that the last layer of the heliosphere shields 75%. We don't really know if this shielding happen in other areas of the heliosphere. We don't even know how it varies with solar cycle and with other conditions. But at least we have one data point showing how important astrospheres and heliosphere are important for life. Next. So this knowledge we learn not only with the in situ data from Voyager 1 and 2, shown here in the top left, but also with global ENA maps by IBEX and Cassini. And I will talk about this data in the next slides. Next. And one of the things to keep in mind that when we are trying to have prediction and understanding of the heliosphere, we come to the realization that our best sophisticated models fail to explain not just any observation, but key observations that describe the heliosphere. Here I'm showing you a panel of flows, the radial flows in the middle panel and the tangential flows in the bottom panel, measured at Voyager 2 in black and in Voyager 1 in red. And you can see that they're very different from each other. And these flows that I'm showing here are in the last layers, the same layer that shield the cosmic rays. This is a region, the heliosheets that I'm showing you the flows. We don't really understand why the flows at Voyager 1 and 2 are so different. And we also, those flows cannot be predicted by current models. So it's a problem. The other problem that I'm going to point out later on in my slides, that Voyagers were not, as Elena said, slotted to probe that region. So they lack instrumentation to measure one of the key particles that carry most of the dynamics and the thermodynamics in the last layers that are pickup ions that I'm going to describe later on. But those are energetic particles around keV, and we don't have instrumentation to measure them directly. So there is a need to revisit this region with interstellar probe. We know that New Horizons have an instrument that measures these particles, but New Horizons won't be able to reach to the interstellar medium. It's going to reach a little bit beyond the termination shock. Next. So let me touch in some basic questions that we don't understand. And this is kind of embarrassing. If you ask yourself, do you know the shape of your house in your neighborhood? Yes, you know, it's a box. And here we are, and we are a very shape of the heliosphere we don't really know. We thought we knew, but in the last years, this shape and this structure is being challenged. So next slide, please. One of the challenges come from data. And you think that data tell you the final answer, but as I will show you, data in different energies give you different answers. So the data come for energetic neutral atoms from Cassini. This was published by Dialinas et al. In 2017, but already pointed out in 2009, that the heliosphere is not a comet-like shape with a tail extended for thousands of AU, like showing in the bottom right, that this is a canonic shape. If you type in Google heliosphere, you will see a comet-like shape with a tail extending for thousands of AU. But the data by energetic neutral atoms point that is not the case, and the heliosphere is a sphere-like. Next. However, if you look at energetic neutral atoms in lower energies, still this is consistent with a comet-like tail. Why is that? We still need to understand. And this was seen by IBEX. Next. Now you said, okay, let me ask the theoretician of the models what they say. What is the shape of the heliosphere? And there is no agreement. So here, if you look on the left side by the Moscow group, here is by Vladis Modenov et al. And on the right side by Nick Pogorelov et al. By the Alabama group, they both get a comet-like shape. And they have different theoretical assumptions, but they get a long tail. Our group is being advocating that the shape is more like a croissant-like, shown here in the middle, very short, almost like tailless. Next slide. One of the things that all the models agree, so this is a relief, at least we agree on something, that the topology of the solar magnetic field is a backbone of the heliosphere. This was kind of a surprise because the solar magnetic field is not the main dynamic actor here, but turns out that in the heliosheath, the pressure of the magnetic field is comparable to the flows that are very slow. So the solar magnetic field turns out to really shape the structure of the heliosphere. And I'm showing here on the right-hand side, the magnetic field in gray by the Nick Pogorelov et al. Model, and in the left by our model in white. And both structures you can see are almost identical. The magnetic field behaves like a slinky bent by the pressure of the interstellar medium. And all models, including the Moscow model, show that the magnetic field confined the solar wind in the heliosheath. So this is a new understanding. Next slide. However, what the consequences of that confinement still need to be understood. We advocated in 2015 that they'll behave like jets, that they're confined, and the interstellar magnetic field, as shown here in the red lines, flow between the heliosphere that is shown in yellow, that is like a croissant-like, and the heliosphere is almost tailless in the sense that the solar magnetic field shape the heliosphere in a croissant-like structure with a distance comparable to the nose and to the tail. Next. Another problem that models are facing, not just the very shape, but how big is your house basically, and how thick is your heliosheath. This is the same heliosheath that shield the galactic cosmic rays, and all the models, no matter what recipe you put in it, we are predicting thicknesses that are a factor of 2 wider than the observations. And even if you include the fact that the solar wind breathes in and out and time-dependent effect, you cannot reconcile this fact. So it's indicating something exciting, that there is some physics that is missing in all the models. We are missing something in our understanding of the heliosheath. Next. The other problems that we're facing, not just that we don't know the shape of the house, the thickness of the house, now we don't even know if the walls of the house, the heliopause, are porous or not. It's almost like you're sitting in your house and you don't even know if the weather is going to be cold or hot, because you don't know if the heliopause is going to shield particles or not. If you look here in the passage of the heliopause by Voyager 1 shown in left, and the passage of the heliopause shown by Voyager 2 on the right, they're very different. I'm not going to go all the details, but these panels show how much the galactic cosmic came into the heliosphere and how much the solar particles on the bottom panels leaked out. And in some cases, like Voyager 1 was very leaky. In cases of Voyager 2 was not leaky. Why is that? So it means that, again, the properties of the heliopause are not understood, and we don't have a predictive models to predict the characteristics of the heliopause in all latitude and longitude with different solar wind conditions, for example. Next. The other fundamental question that I touched in the beginning is about the pickup ions. The pickup ions are particles that are not the thermal component of the solar wind that is cold, shown here in this complicated plot, but what suffice for you to understand that the blue region in this plot show the intensity of particle per energy that the Voyager is blind. Voyager measure the pieces that are to the left and to the right of this blue box. But we think the particles on that energy range are the ones that play the key role in the heliosheath. But Voyager doesn't have an instrument to be able to measure that. Next. What we did learn, and this is why we know that the pickup ions are so important, that when the solar winds slow down with respect to the galaxy and become subsonic, it's go from a very fast flow, 400 kilometers per second, to a slow, 100 kilometers per second, that shock transfer 80% of the energy, not to the thermal cold plasma, but to those energies that the Voyager is blind, the pickup ions. And this is shown in this beautiful plot that John Richardson et al. Published about the crossing of the termination shock. The prediction, if all the energies would have gone to the cold particles, would have been that the temperature would be like the black diamond shown in the bottom panel. But in fact, the measurements show an order of magnitude cold. This is a cold plasma. And when you calculate, you realize that the rest of the energy is hidden in this spot where Voyager is blind. Next. However, if you use your best understanding how the pickup ions are evolving, and here we use some measurements, very beautiful measurements that New Horizons is making at 40 AU from the sun. When you include them as a separate fluid in your models, you separate the thermal and the pickup ions, they have a major effect. So our croissant that we had a prediction, when we include the pickup ions, they become energetic neutral atoms and leave the system deflating the heliosphere. So it's almost like you're deflating your balloon, and the heliosphere, it's still organized by the magnetic field, but it's very spherical at the nose. And so you can call it a deflated croissant. But in any case, what is interesting that the nose of the heliosphere is very spherical, starting to look like the energetic neutral atoms in high energies. Okay, next. But what we don't have in our models, and neither we do have an understanding, and how different processes like reconnection, like turbulence, like acceleration of particles affect pickup ions. Neither in the supersonic solar wind, neither in the heliosheath where the solar wind becomes slow. Those are processes that you can theoretically simulate and calculate, and you know that they can affect pickup ions, but we still don't have a fully understanding what the effect is and how to incorporate in the models. We also don't have the instrumentation on Voyager to really uncover if reconnection is happening or not, or neither to measure if turbulence is happening. So this is, again, another reason why to come back to that region with a modern instrumentation. Next. And another question related with the pickup ions, that there is an old paradigm that the pickup ions are carried by the solar wind, they come to this gigantic termination shock, and they're accelerated to MEV energies, what we call anomalous cosmic rays. And if you look on the left panel, those are intensity of particles per energy. And this is a diagram almost like when you have a diet, so before and after the diet. So this is before the termination shock crossing, after the termination shock crossing. And if you look at the piece of the anomalous cosmic rays, you cannot even tell that there was a shock. So what happened was a major surprise. And next, that the intensity of the anomalous cosmic rays didn't really change at the termination shock at around MeV. And this complicated panel here by Alan Cummings show that the intensity of the anomalous cosmic rays continued to increase until the heliopause, until it's dropped once we left the heliosheath. So it seemed like those particles are accelerated in the heliosheath or somewhere else in the termination shock, not close to the Voyager 1 and 2 spacecraft. And this has really broad implication, like many other questions that I touched already, for astrophysics as well, and for space physics in general, for do we understand acceleration of particles in shocks, for example. Okay, next. Now that I touch on the broad existential questions of our understanding in the heliosphere, we come to the last piece, that how the heliosphere interacts with interstellar medium. So if you would have asked us before Voyagers crossed to the interstellar medium, we might have predicted that locally, just outside the heliosphere, the interstellar medium will be somewhat quiet. But this is not the case. Next slide. And what the Voyager 1 and 2 spacecraft uncovered, and this is a beautiful panel by Don Gournett, that show that this is the plasma measurements ahead of the heliopause on Voyager 1. And for all the time, still now, you can extend this plot further, and Jamie Rankin is going to talk more about it. There are several shocks shown in the top panel, and these green and red blobs that intercept the interstellar medium. They're perturbation that we think driven by the solar wind. We don't really understand that, but it shows, if you see the intensity of particles, they're not isotropic, they're anisotropic. It means that the solar wind continue to influence the interstellar medium region quite substantially for at least 30 AU ahead of the heliopause. we don't really know how far this influence extends. And this, again, it has a broad implication for how stars in general interact with the interstellar medium. So again, we need an interstellar probe to go out there and go way beyond 30 AU to really probe that region. Next slide. And the last question too, not just how far we perturb the interstellar medium, but what happened with the magnetic field that comes from the galaxy? How does it change and drape around stars and astrospheres and heliosphere? We had a prediction that the magnetic field out there is very different than the solar-like, and it's going to rotate pretty dramatically as it reaches the heliopause. And this was one of the signatures that we waited. As soon as we will go out of the interstellar medium, we will see a rotation of the magnetic field. And next slide. And in fact, what we saw is nothing like that. It's similar to the anomalous cosmic ray story. If you would be just looking at the magnetic field angles shown here in lambda and delta that give you the direction, before and after the heliopause, this angle barely change, and they are solar-like. It's like the magnetic field in the galaxy outside in the local interstellar medium is solar-like. When it's going to rotate to its original direction, we don't know. And how far we have to go to start seeing this rotation, it's another open question. So I want to leave you, next slide, with just an idea to think that a proposed trajectory of an interstellar probe, I will advocate should go through the flanks. Not through the nose, that we still have a lot of mysteries to uncover, but it will be a new region in space that neither Voyager 1 and 2 left. We will probably discover a new region in space with flows and particles. If we revisit it with an instrument that can measure pickup ions, it would be amazing. We will be probing the draping of the interstellar magnetic field and probably where the anomalous cosmic rays are accelerated. So I will leave you with that. I already made my point that we need to revisit that and pass it to Jamie Rankin. Thank you.
Thank you very much, Professor Ofer. And now for Dr. Jamie Rankin's presentation.
Thank you, Merav. Thank you, James. Today, I'm going to talk about solar transients through the heliosphere and beyond, and how they uniquely enable us to view our bubble between the stars, not only from the inside out, but also from the outside in. Next slide. The plot on the left is my favorite summary of Voyager's journey through the solar system, taken by Voyager 1, using cosmic rays, which are particles energized by external sources that are spread throughout the galaxy. Time is shown on the horizontal axis. And remember, both Voyagers are moving further and further outward, so time represents increasing distance from the sun. And then count rates are shown on the vertical axis. These are the number of cosmic rays that are detected at the spacecraft in a given second. As Merav mentioned earlier, this plot illustrates how much the heliosphere shields us from external radiation. From 1977 to about 2004, you can see clear periodic structures indicative of what is called solar modulations. You see cosmic ray intensities behave opposite to the solar cycle. They peak at solar minimum when the sun's output is the weakest, and they dip at solar maximum when the solar output is the strongest. And the overall periodicity matches that of the solar cycle, which is roughly 11 years. Around 2005, beginning of 2005, Voyager crossed the termination shock and arrived in the solar wind's subsonic region, known as the heliosheath, where the pattern is no longer obvious. But we do still see a clear trend of cosmic ray counting rate that increases as Voyager 1 moves away from the sun. Finally, towards the end of 2012, Voyager 1 crossed into the interstellar medium. We can see that from the inset plot on the bottom right. And you can see that the cosmic rays are very steady and quite unchanging compared to those preceding measurements. So this begs the question that's captured on in the cartoons on the right-hand side. What's out there that's interesting in interstellar space? Is it simply a vast cosmic emptiness filled with lots of cold, uninteresting particles? Actually, to our surprise, we found that this region, which we call the very local interstellar medium, is still highly influenced by the sun, despite the fact that we have now crossed beyond the sun's material and plasma boundary. Next slide. One example of the activity out there was captured by Voyager 1's radio instrument, which directly saw emissions caused by unstable beams of electrons. Large radio emissions similar to the events shown here were first seen back in the 90s, early 90s by both Voyager spacecraft following major solar events. And these emissions were amongst the first hints of unusual activity occurring far beyond the outer planets. Next slide. Another example of time-varying changes in the very local interstellar medium occurs in the magnetic field. Although the direction of the field did not change when Voyager 1 first arrived, the field's strength does vary due to shocks. And as we can see most clearly from the top panel of the plot, there's an onset of 2 large shocks marked by the vertical lines in front of sections 2 and 4. So there's a sudden increase in the magnetic field. And although some aspects of these shocks may seem familiar to those who study such things closer to the sun, they're also strange, quite strange. They're very weak, and they're thousands of times thicker than their near-Earth counterparts. And the rise in the magnetic field takes 3 to 5 days, whereas closer to the sun, that might only take minutes. Next slide. We also see evidence of how both low and high energy particles get energized by these very weak shocks. In fact, that's how the radio emissions are produced. Beams of low energy electrons gain energy at the shock's boundary. Don Gurnett and collaborators showed in 2015 study that, and hypothesized that particles could be energized in this similar way, both low and high energy particles. And they drew from analogous effects observed much closer to the sun. The diagram on the top left shows that as a spacecraft approaches one of these shocks, it will encounter field lines that are connected to different places along the boundary. And particles energized by the shock will travel along the field lines and eventually reach the spacecraft and be observed well before the shock itself arrives. Evidence of this timing is shown in the plot on the right. The top panel depicts the cosmic ray of protons, and the middle panel shows electrons, both millions of times higher in energy than the plasma electrons responsible for the radio emissions shown in the bottom. And you can see that the cosmic rays arrive first in the top and middle panel, and then the spikes of the plasma oscillations in the bottom. And then eventually, even though it's not shown, the shock itself crosses the spacecraft. Next slide. Finally, there's the unanticipated discovery of cosmic ray anisotropies. And this is the topic of my thesis work at Caltech under Dr. Ed Stone. Near the sun, it's not uncommon for cosmic ray intensities to be reduced following a shock event. Although these are analogous, they're also very unusual because the intensities appear steady state normal in all directions except perpendicular to the magnetic field. The top panel illustrates this using the LECP instrument on Voyager 1, which consists of a double-ended telescope that steps in 45-degree sectors. And you can see that the intensities in the red and green are very steady, except for occasional shock spikes, while the intensities in blue, which is when the telescope is pointed perpendicular to the magnetic field, they show unusual variations that last from 250 to over 600 days. And the middle plot shows an all-sky view from detectors on a second cosmic ray instrument, CRS. And so we have 2 instruments that agree about the structure and the statistical significance of this never-before-seen physical phenomenon. The bottom panel shows the view from one of the fixed telescopes on the CRS instrument, and that telescope happens to be pointed just off from the magnetic field, and it doesn't see any effects from the anisotropy. But we do see occasional dips that occur during spacecraft calibration maneuvers. And during these maneuvers, the telescope does happen to overlap with that 90-degree pitch angle region in its view. Next slide. In fact, using these calibration maneuvers, where the spacecraft rotates about its sun-facing axis, we were able to confirm that the dropouts are in fact centered on 90 degrees with respect to the magnetic field. And we also showed that this region And so that you can see that with the red line. And we also showed that this region of affected particles is roughly 20 degrees wide. It appears that all particles outside of that are unaffected. And although for the most part, these events appear related to the passage of weak shocks, many details of their underlying physics remain unresolved. Next slide. This plot shows views of different telescopes on the same instrument, CRS, during other periods of spacecraft repointing. The black, blue, and green lines were taken by a telescope that points just off of the 90 degrees during these particular maneuvers. It measures low and high energy protons, which are blue and black, and then low energy electrons, green. The plot in the red was taken by a telescope that's solely dedicated to measuring electrons, and that happened to be pointed directly at 90 degrees. In short, we find that electrons that are in the green and the red are not experiencing the anisotropy, while protons in the black and blue are seeing it. We do not know why this is. Next slide. So here's a summary of these transient events. What causes these disturbances? The answer is the sun. As solar events, flares, coronal mass ejections, and other types of solar energetic particle events sweep out from the sun, the quickly moving ones overtake the more slowly moving ones and merge into large structures. The resulting merged interaction regions can survive out to the heliopause and transmit pressure waves into the interstellar medium. This in turn produces the disturbances I've described. So even beyond the sun's material and plasma limits, we see many examples of how the sun influences its surroundings in surprising ways. Next slide. So how do we know these events come from the sun? Here we step back from the interstellar medium and place ourselves just on the other side of the boundary in the heliosheath. Focusing on the left figure, Voyager 2's working plasma instrument found evidence of these merged events, and in terms of large pressure pulses in the plasma. The plot on the right is a simulation which takes events from the sun and propagates them all the way out to the interstellar medium. These simulations could actually recreate the timing of the shocks and radio missions of Voyager 1. They even successfully predicted a follow-on event. Next slide. In fact, we have evidence of an event that first crossed Voyager 2 in the heliosheath and disturbed the cosmic rays shown in the blue plot on the bottom of the figure. The structure then went on to transmit a pressure wave into the interstellar medium, which arrived at Voyager 1 only 130 days later. That's the top in the red. In fact, these two cosmic ray profiles showed a 91.2% similarity. And beyond this really cool finding, we used the observations to infer a never before measured quantity, the heliosheath's total pressure, which when balanced with the interstellar wind establishes the size of the heliosphere. Next slide. I'm not going to spend too much time here, but this enables an exciting side-by-side snapshot of the effects in the heliosheath on the left compared to the effects in the interstellar medium on the right. I'll quickly point out that even though the cosmic ray profiles on the top, A and D, are very similar, the effect of Voyager 2 was seen from all directions in the sky, while at Voyager 1, it was only isolated to that specific region I just described, centered at 90 degrees. Why is this? We do not know. Next slide. Finally, the Interstellar Boundary Explorer, IBEX, which remotely images the heliosphere's global boundaries, recently observed the effects of a substantial increase in the sun's output. You can see that in the step up in the bottom plot in red around mid-2014. And that substantial increase later pressurized the heliosheath. And you can see that captured in the top right sphere in that red region. And this continues to inflate various regions of the heliosphere to this day. So we have global observations that show the effect. What do the Voyagers see? Next slide. That particular event was the largest of these pressure pulses in the heliosheath seen by Voyager 2. And it was later seen as a very strange magnetic disturbance, unlike the prior shocks at Voyager 1. So the magnetic field had a 35-day rise time and then a 340-day kind of gradual change. And we've never seen anything like this before. Next slide. So we live at a very exciting time where there's a lot of activity and a lot of open questions about what's happening in the interstellar medium. And there's a whole selection of these that are just here for reference, but next slide. Regarding what I've discussed today, I think some key ones are how far into the interstellar medium can these transients be observed? And why are there anisotropies that are beyond the heliopause, but not in the heliosphere itself? And why do cosmic ray electrons behave so differently than the protons out there? And what new things can we learn about the fundamental physics in the interstellar medium? And this opens a whole lot of opportunity for exciting science on Interstellar Probe. Next slide. And this is just kind of an overall list with some details, but I think some of the most exciting things are the opportunity to monitor space weather, not just close to Earth, but beyond the entire heliopause. And it's an opportunity to also connect to the broader heliophysics fleet. And we can provide in situ context for global observations. There's a new mission that will map the outer boundaries called Interstellar Mapping and Acceleration Probe, due to launch in 2024. And it's important to have both the combination of these global observations and the in situ measurements. And we can also watch the heliosphere evolve just under very different solar cycle conditions. And we can uncover yet to be understood properties of the heliosheath in the interstellar medium. Thank you very much.
All right, thank you very much, Jamie, Merav, and Elena, for your wonderful presentations. We're now going to go to the question and answer session. So we have a few questions that Merav, you had answered, and I'd like to discuss those with everyone here. So the first question was, does a trajectory through the flanks aid the modeling sufficiently through the nose, or does it offer more interesting region for dynamics as posed by the models? Merav, I was wondering if you could address that.
Okay. Thank you, James. So I think why I advocated for going through the flanks is because Voyager 1 and 2 left the heliosphere very close to the nose. Voyager 1 exactly at the nose, and Voyager 2 30 degrees, but still very much within the nose. So flanks will need to go much more, like 60 degrees or more. So that region is interesting for many reasons. One of them, we think by several models that the origin of the anomalous cosmic rays, whether it's coming at the heliopause or whether it's coming near the termination shock, it's coming from the flanks. We can see some new measurements that show that they're streaming toward the spacecraft from the flanks. So this would be one reason to really probe in situ much closer to the origin of the anomalous cosmic rays. The other one is that if you really want to study the shape of the heliosphere, if you go through the nose, you look back, you can see the shape. So if you go in the flanks, you can have energetic neutral atoms detector there, or even just understanding the plasma behavior and the draping of the magnetic field will allow you to constrain, again, with in situ measurements, what is the shape of the heliosphere. And lastly, there is also the question about how the magnetic field from the galaxy drape around the heliosphere. And we think that this is changing to a solar-like direction from some effects and phenomena happening at the flanks. So again, we will be able to probe by going to that region.
Thank you very much, Merav. And then could you comment on the second question, which was how much of the galactic cosmic rays are shielded by the heliosphere and how much by Earth's magnetic field? And hence, how important is the heliosphere really for the emergence of and evolution of life?
So, right. So as I showed in my plot, I think with the second slide, with the galactic cosmic rays varying the intensity with the solar cycle, there are some peaks and valleys as Voyager went, But the major jump, the 75% shield, happened after the termination shock in the last layer in the heliosheath. So it means that the astrosphere or the heliosphere, the heliosheath is a crucial filter for the galactic cosmic rays. Something does happen within the heliosphere and further by the magnetic field of Earth, but the main shielding, that 75%, happened at the heliosheath, the last layers.
Thank you very much, Merav. And then Jamie, a couple questions for you. So the first one by Stephen Talbot. How does the interstellar probe require a certain specific set of measurements continuing by a future heliophysics fleet?
Well, my statement was mostly saying that there's an opportunity, a very exciting opportunity, that when interstellar probe gets out there, there is a fleet that's constantly observing the sun. And so if we see an event like this pass, we can know when it arrives at different places with whatever fleet is out there, and then eventually track that out there at interstellar probe.
Okay, thank you. And then for the next question by Christopher Rose, for you, Jamie, as well. Do we have any sense of how neutrino density or behavior might change from the heliosphere to the interstellar medium?
Nope, we don't have any neutrino detectors. It'd be a neat thing to do, but I don't know that any have been flown.
Okay, all right, thank you. And now we have another question. And this is for you, Jamie. Will it be possible to differentiate in the particles related to the CIRs from that of the solar transients using interstellar probe observations outside the heliosphere?
That's an excellent question. The last event that I showed that was seen in IBEX was an example of something that's not just a CIR. So that event did show unusual signatures at Voyager compared to these other transients, which are emerging of multiple CIRs. So possibly by studying that event a lot more closely, which is ongoing, we'll be able to tell the key variables that discriminate just these passing ones from whole changes to the solar output. However, it's important, I think, to have some sort of mapping, global mapping picture, because that's the easiest way to be able to tell the difference.
I can just add one thing to what Jamie's saying, that in terms of modeling and theory, and Elena is an expert on that as well, we don't really understand the evolution of CIRs and neither shocks all the way from the sun to the interstellar medium. We have some idea how they merge and evolve, but we don't have it, really understood that we can really probe one by one which shock generated which signature in the ISM.
Thank you very much, Jamie.
Yeah, and if I can maybe add, James, to this, as these structures propagate through the interface, through the termination shock and heliopause, interaction of CIRs and associated shocks and CMEs or global merged interaction regions with their shocks, as they go through the interface, they generate more structures. And it's really, difficult to extract the original structures and those that are newly generated.
Thank you very much, Elena. I'm looking at the question and answer panel now. I don't see any new questions, so I'll wait a couple of seconds. All right. So thank you very much. That's all the time we have for today. So first, I'd like to thank all of our panelists, and I'd like to thank you for attending today's webinar. Our next webinar will be on Thursday, June 25th at noon Eastern Time, titled Imaging the Heliospheric Boundary, where we will have a panel presentation by Pontus Brandt, Kostas Dialinis, and Eric Camareras. Please visit the Interstellar Probe website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv using the community involvement section of the website to make sure you are getting the latest information on upcoming webinars and events. Thanks for joining us and have a wonderful day.